In section 4.1, we're going to encounter the area problem and how we solve the calculation of area under a curve. Throughout this section, I might use the following summation notation. This letter stands for capital sigma, and it has an I equals M on the bottom and an N on the top. And the sigma symbol tells us to add together term by term. The lower number, the I equals M, tells us the number to start with, and the top one tells us the number to stop counting for with N. So we read this as the summation I equals M to N. This particular setup here has f of xi times delta x. The expansion of the summation starts with f of x sub m delta x plus f of x sub m plus 1 delta x plus all the way up to f of x sub n delta x. So the real thing to look at here for is the sum. We're adding term by term, and the fact that the subscript numbers start with m and count up to n, whatever those numbers might be. For example, here's a slightly simpler example. Summation I equals 1 to 10 of I means to start I with 1, then count to 2, to 3, to 4, all the way up to 9 and to 10, adding together each term one by one into one long summation statement. As part of using the summation, we're going to be using some summation formulas at times. So here are summation formulas that we might refer back to. So we're going to use the idea of summations in the consideration of the problem of estimating the area under the parabola, in this case y equals x squared, from 0 to 1. So we'd like to figure out what's that area here inside the curve, underneath the curve, between it and the x-axis. One way of approximating it is by using rectangles placed inside or on the curve. This first one here we call the left endpoints. I refer to it by left endpoints because I'm placing the left upper corner of each rectangle on the curve. This is in contrast to right endpoints, where I put the upper right corner of each rectangle on the curve. So each of these setups are an approximation of the area under the curve. One is a slight under approximation, leaving some area out, and the other is a slight over approximation with areas going outside of the curve. So to figure out what areas we get from these rectangles, we'll notice that this is set up with 3 rectangles, and each one has a width of 1/4. The height of each rectangle can be determined by taking the left number at the bottom of the rectangle and plugging it into the function. So in this case, since it's the x squared function, the height of the first rectangle is equal to 1/4 squared. The height of the second rectangle is 1/2 squared. And the height of the third rectangle is 3/4 squared. And then what we can do is add together the areas of each rectangle, and I do this by doing the formula for rectangle width times height. And so 1/4 width times 1/4 squared, which is the height of the first rectangle, plus 1/4 times 1/2 squared, that's width times height of the second, and then width times height of the third, altogether adds up to be 7/32. And that's approximately 0.21875. So this estimation of area places the area around 0.21875, which we can tell is an under approximation of the area, leaving out some of the area on the inside. Let's see how this compares with right endpoints instead. In this case, the height of the first rectangle is 1/4 squared, then 1/2 squared, 3/4 squared, and the last one would be just 1 squared. So we have 4 rectangles here. The area adds up, when we put them all together, width times height, and add them, to 15/32. So this is bigger than it was with the left endpoints. We get 0.46875. which is an over approximation of the area under the curve. Now, how we could do this better is if we increase the number of rectangles, and then we leave less space inside, or we go a little bit less over on the approximation of the area. So this picture here shows what it would look like with left or right endpoints with 8 rectangles. But let's make a table. If we continue to go higher and higher in the number of rectangles, the number of rectangles n starts from 10 to 20 and goes all the way up to 1,000. Then these two columns over here stand for the sum of the areas of the left and right rectangles. Notice how the numbers are slowly getting less apart. So the approximation from either way is getting closer to the actual area inside of the curve. So as the number of rectangles increases as n goes to infinity, in other words, we can consider the limit of the sum of the rectangles is approaching to a number. And that number is going to ultimately tell us what the area under the curve is. So now we're getting into the idea of taking areas, summing them, and using limits to actually get the exact area inside of the curve. And this gives rise to the definition of the area under a curve. This is going to be a definition using the right rectangles, but this is similar for other cases as well. So we say the area A of a region S that lies under the graph of a continuous function f is the limit of the sum of the areas of approximating rectangles. Here I'm writing it as A is equal to the limit as n goes to infinity of R of n. R of n stands for the right corner rectangles. And so we could write this as the limit as n goes to infinity of f of x1 delta x plus f of x2 delta x plus all the way up to f of x to the n, f sub n delta x, where delta x stands for the width we see in the illustration of each rectangle, and f of xi stands for the height of each rectangle. So this is a general definition for any function using the approximating rectangles to calculate the area inside the curve by taking the limit as the number of rectangles goes to infinity. In this example, we're going to continue our discussion here on the function. We're going to show that the sum of the areas of upper approximating rectangles approaches 1/3. That is, the limit as n goes to infinity of r sub n is equal to 1/3. Now we're still going to be dealing with the function y equals x squared from 0 to 1. And so let's visualize what's going on here. We're going to make some rectangles. They call them right rectangles. So I'm going to put the right corner here on the curve. So we're going to have, in general, n of them. So our first one would have width 1 over n, 2 over n, 3 over n, all the way up to the very last rectangle, which is over here at 1, which would be the same thing as n over n. Now again, we'll be able to tell the width. The width in general is b minus a over n, where a is equal to the start of the interval and b is equal to the end of the interval. So in this case, we're dealing with the interval from 0 to 1. So that's what I'm considering the a and the b in this case. And so it would look something like, under that conditions, 1 minus 0 over n, or just 1 over n. So we're going to, again, let r of n stand for the sum of the areas of the right rectangles. And so if I add them all up here, we consider what the height again of each of our rectangles are. The first one would have height 1 over n squared, and then 2 over n squared, 3 over n squared, all the way up to the last one here, which would be basically n over n squared, or just 1 squared. So r of sub n would be equal to 1 over n times 1 over n squared. And what I'm doing here again is width times height plus 1 over n times 2 over n squared plus 1 over n times 3 over n squared plus dot 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 all the way up to 1 over n times n over n squared. Now, in order to handle this summation, what I'm going to do is factor out a 1 over n. Because notice how 1 over n is a common for all the terms in the summation. So we can write it as 1 over n, and we'll go ahead and write the inside as 1 squared over n squared plus 2 squared over n squared plus 3 squared over n squared plus, and so on, dot dot dot, all the way up to, and we'll just write this as n squared over n squared. And I can take this even a step further by noticing how there's a common factor of n squared across all these terms. So let's rewrite this as 1 over n. We'll factor that out as 1 over n squared times 1 squared plus 2 squared plus 3 squared plus dot 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 all the way up to n squared. Okay, and then we can write that as 1 over n cubed times, and then I'm going to write this summation from 1 plus 2 plus 3 each squared as the summation I equals 1 to n, that's the counting values for each term, of I squared. That's how we can write the summation of all of this stuff here. Okay, we have a formula for this particular summation here. And what that formula tells us about our summation is that we can rewrite that whole summation as n times n plus 1 times 2n plus 1 all over 6. Now what I'll do at this point is reduce down a factor of n from top and bottom with that other fraction in front. So we can rewrite this as n plus 1 times 2n plus 1 all over 6n squared. And so I'll go ahead and multiply through everything on top, expand it out, and it would be 2n squared plus 3n plus 1 all over 6n squared. Now what we do in order, this is the sum of n rectangles, but to get the sum of as the area under the curve, we have to take the limit as the number of rectangles goes to infinity. So we take the limit as n goes to infinity of r sub n, which is equal to the limit as n goes to infinity of 2n squared plus 3n plus 1 all over 6n squared. In an earlier section, we covered how to evaluate this type of limit. Basically, what we can do is divide all terms by the highest power of, divided by the highest power of n in the denominator. So we're going to divide through everything by n squared. That way we can reduce this thing down a little bit and evaluate the limit. This limit would equal to the limit as n goes to infinity of 2 plus 3 over n plus 1 over n squared all over 6. And then those limits on top, these 1 over n squared and so forth, those things are just going to go to 0 as n goes to infinity. So the limit is equal to 2 plus 0 all over 6. or that would just be 1 over 3, which is what it mentioned that it should come out to be. So by this limit, we now know exactly, precisely, the area under the curve of y equals x squared between 0 and 1 is 1/3. On this next example, we're going to take a look at a function just f of x equals cosine x between 0 and b, where b is between 0 and pi over 2. What we're going to do is find an expression for the limit of the area under the curve. We're not going to evaluate the limit, but we'll find an expression for that limit. Now, it's helpful to recall what the cosine does. Its graph starts at 1, goes down to 0, goes up, and comes back up to 1 again as we move between 0 and 2 pi. Let's zoom in on the area here from 0 to pi over 2. So in between there, we'd like to position the number b. It can be anywhere from 0 to pi over 2. It says up above. And what we're going to do is, using right endpoints, we're going to construct our rectangles and the limit to figure out what the area would be under the curve. So if we imagine our rectangles kind of positioned like this inside, I don't know how many will be in there necessarily, but just an idea. There will be a total of n rectangles. And so let's label the endpoints here for x1, x2, x3, all the way up to xn, which will be the same thing as b at the end. Up here at the top is the starting number, which in our case is 0, but that's also referred to as a. So we're going to refer to the width of each rectangle here as delta x. How we calculate delta x for the width is b minus a over n. So in this case, that would look like b is the last number, unspecified number, minus 0 over n, so it'd just be b over n. So what we can determine is that our first one, x1, would be b over n. Our second x2 location would be 2b over n. Our x3 would be 3b over n, all the way up to the last one, xn, which would be nb over n, or just b. So our summation here for the sum of all the right rectangles would be f of x1 delta x plus f of x2 delta x plus f of x3 delta x. This is again width times height for each rectangle, plus all the way up to f of xn delta x. So in the context of our function is cosine, so it would go cosine of b over n times b over n plus cosine 2b over n times b over n plus cosine 3b over n times b over n plus dot 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 all the way up to cosine nb over n times b over n. Now I'll go ahead and simplify the summation down by factoring out this b over n from each of the terms. So we're going to make it look something like b over n times cosine b over n plus cosine 2b over n plus cosine 3b over n, and so on, all the way up to cosine of nb over n. To make this look a little bit more compact, I'm going to write this in summation notation. Okay, where we can notice how it counts up 1, 2, 3, all the way up to n. So how we write this in summation notation is b over n times the summation I equals 1 to n of cosine IB over n. So notice how I put that I in front of the b. That's the number that's counting, and that's how we write the notation to indicate that I goes from 1 to n in this summation. So this is an expression of the area of the summation of the area of the right corner rectangles. Now this next one says, estimate the area for the case where b is equal to pi over 2 by taking sample points to be the midpoints and using 4 subintervals. So far I hadn't shown what it meant by midpoints. We've used right and left rectangles so far, but we can also use really any location we'd like to position things. But midpoint means the middle of the rectangle is positioned on the curve. So there's a point on the curve located at the top, and the top is at the middle of each of the rectangles. So we can do this in addition to the right and left corner rectangles. In a way, it's a little bit nicer because we don't always go over or under. It kind of splits the difference. Okay, so for our cosine function, let's set up the midpoint rectangles for this one. So I'm going to set this up with 4 equal segments. How we figure out the width of each of these segments, we're going to consider that n is equal to 4 for 4 rectangles, and b is equal to pi over 2 for the end of the interval. So delta x, the width of each rectangle, would be calculated by b minus a over n, which would equal to pi over 2 over 4. Or I guess more precisely, I should write that as pi over 2 minus 0 over 4, since a is equal to 0. So delta x would be equal to pi over 2 times 1/4, or pi over 8. So let's lay out the numbers here. We'll have pi over 8, 2 pi over 8, which is basically pi over 4, in other words. 3 pi over 8, and then there'll be 4 pi over 8 at the end, which that's the same thing as pi over 2. And then what we're going to do is create our rectangles, but we're going to do this in the middle of each of our subintervals that we've set up here with the rectangles. And so the numbers in the middle here would be pi over 16, 3 pi over 16, 5 pi over 16, and 7 pi over 16. We can figure that out if you're curious by taking, say, the pi over 8. That's like 2 pi over 16. So if you count in pi over 16s, it would look something like this. So what we're going to do the midpoints, I'm going to use m sub 4 to stand for the sum of the 4 midpoint rectangles. So m sub 4 would equal to f of pi over 16 times the width, pi over 8, plus f of 3 pi over 16 times pi over 8, plus f of 5 pi over 16 times pi over 8, plus f of 7 pi over 16 times pi over 8. Okie doke, and so this is equal to pi over 8. We just go ahead and factor that out, times Then f of pi over 16 would be cosine of pi over 16 plus cosine 3 pi over 16 plus cosine of 5 pi over 16 plus cosine of 7 pi over 16. Okay, and then I ran through the calculator through that, and it comes out to be approximately 1.006. So using midpoint rectangles, this is an approximation for rectangles of the area under the curve between 0 to 2 pi. On example 4, we're going to be looking at this function f of x equals 1 over 1 plus x squared on the interval from -2 to 2. We're going to estimate the area under the graph using for approximating rectangles using right midpoints and midpoints. So I'll show you all a picture of how this looks in each case. So our function is going to do something like this. It kind of comes up here, then it goes down from there. We're looking at the interval from -2 to 2. All right, we're going to use right endpoint rectangles, and we're going to use 4 of them. So it actually makes it pretty easy using the interval we're dealing with here. We already have kind of 4 different segments set up. So we'll just be setting it up like this. So -1, 0, 1 are the numbers so far. Now for midpoints, on the other hand, we kind of have to go in the middle between the numbers. So this is how we're going to set up the height of each of our rectangles. And so those would be positioned here in the middle at like -1.5, -0.5, 0.5, and 1.5. So in any case though, delta x, which is the width of each rectangle, which is b minus a over n, would be what we just were looking at up above, but to calculate it, it would look like 2 minus -2 over 4, since we're doing 4 rectangles, and that's just equal to 1, which makes sense versus what we just did in the picture. Okay, so the right endpoint rectangles add together by doing f of -1 times 1 plus f of 0 times 1 plus f of 1 times 1 plus f of 2 times 1. Okay, and I won't go through plugging in all these things, but basically f of -1 in this particular function would look like 1 over 1 plus -1 squared, which would equal to 1 over 2. And we could do that for all of them here. So it looks something like 1 over 2 times 1 plus, look like 1 over 1 times 1 times 1 over 2 times 1 plus 1 over 5 times 1. And I went ahead and got a decimal for all this, not approximately, it's actually equal to exactly 2.2. Now, if you'd like to practice this on your own, see if you can set up and find the midpoint rectangles, in this case, the area with those rectangles. So I'm going to set that up for 4 rectangles. It'll go f of -1.5 times 1 plus f of -0.5 times 1 plus f of 0.5 times 1 plus f of 1.5 times 1. Now, this is a little bit trickier, but not that much harder necessarily. I went ahead and just plugged that all in the calculator and got out approximately 2.2154 for the area.